Welcome everyone. This is our first Brain Hackers Meetup, totally experimental, and I'm really happy to see actually a good show up, I think, from our expectations.
It's alright.
Yeah. So why did we start Brain Hackers? What I think, we see a lot of cool technology out there in the world that can be used to better understand our body and mind. There's neurotechnology, lots of biosensors, quantified self, all kind of robotics and that kind of stuff. And I think on the intersection of all those fields, we see a lot of things happening, and we want to, connect you all in all of these fields. So, for example, in Eindhoven alone, I tried to list all the projects that I could find in these kind of adjacent fields. So there are people doing lots of personal things, like trying to predict their own epilepsy attacks and all those kind of things. So that's really cool. And there are also lots of companies trying to build products. So there are companies like OSINT I found here in the area. They do gamified rehabilitation, so using biosensors and bionics to help you get rehabilitated. There's things to predict and prevent headaches. There will be 2 talks today from startups in this field, and a lot more. But all these different projects, they're not really well connected, you have a feeling, and I think we can learn a lot from each other, all the personal and startup projects, and maybe start new projects from there. So that's kind of our goal with this meetup, right? We find all the isolated cool projects in this area, find each other. Maybe we can also connect you to already running projects, or maybe you can start new projects, or we can connect bigger projects together, all in this AI, neurotech, biosensor, brain fields, all to improve our own body and mind. Yeah? This is kind of our goal. So, and of course we're looking forward to your input. So one of the projects that started now is us. So we are the Brain Hacker organizers. 3 of us are here right now. We've got me, we've got Martin sitting over there, and Zera there in the back. Well, if you want to help, if you really believe also that this is a cool thing to do and to grow further, we're looking for more volunteers to help us. So yeah, that's already one feedback to you guys. And then we're also looking for things that we could do, right? So we can do these meetups just to find each other, all the other kindred souls, and to just share knowledge. But we can do many more cool things. We could do hackathons on real problems. I've got, so for example, I've got biosensors at home, and I know other people have biosensors. We could just get together, get inspired, and see what we can do with all this technology. We can even hack together entire embedded sensors and things, whatever is interested to do. We had the idea to maybe host an ideation workshop, to find more ideas. So then definitely we need some volunteers for that. And we are looking for your thoughts. So definitely will be the question too. So for now we will just do a few inspirational talks, right? To get the juices ready. So that is, we've got these 2 people tonight here. But first of all, so any thoughts from you already? Why are you here? Anyone want to maybe share?
Backgrounds, like what you're into.
Yeah, for sure.
Yeah, go ahead. So yeah, he has started all exactly in this field, So
Quite close to it.
I will leave the introduction to you.
Yeah, so I'm going to tell you something about my background and Mentech and how we founded it, how we built the company. Also a bit about the tech, so what we do. And what I think to capture it in one sentence, we do early stress recognition with the use of wearables and artificial intelligence. So my background is, I joined the company at the beginning. I had a background in electrical engineering and currently also innovation management. Back then we just we found a problem which we would like to solve. That's why the company was solved was founded from a problem that was a real world example, and which we would like to have a solution for. So the idea started with Patrick. That's this guy on the side of the screen. And Patrick is a person with a severe intellectual disability. So he has trouble speaking, trouble communicating also non-verbally, and it's very difficult for an outsider like you or like even the parents to understand how Patrick is feeling and what is going on in his mind and what he would like to do or to have. And one specific example we often use is that, for example, Patrick was not himself. He was at the local fair in the playground, and he was like being agitated. He didn't want it. He didn't like he was not enjoying the rides that much, and nobody knew why. So there was something wrong, but nobody knew exactly why. And then at the end of the day, they took off his shoe, and they noticed his shoe was hurting because now he was himself again. It was Patrick again. And of course, then he had, so he couldn't handle himself, and he was experiencing pain all day. And yeah, that's why we found in Mentex, so can we help these kind of guys with expressing themselves so they can have a better quality of life in the end. And that's also what our mission is currently. So we want to increase the quality of life and happiness of vulnerable people with intellectual disabilities or dementia, like in voice through technology. That's what we do. We do it with a lot of tools, but I will come back to that. So currently we are located in Eindhoven, not at the height of campus, but in Bosdijk. We have the second floor of an office building. We have 30 employees from all different kind of fields. So we have technicians, but also healthcare technologists, psychologists, and everything around that. And they are all very motivated to make a change in healthcare because there are lots of big shortages of staff. We'd like to have a solution for that. Small picture of our team, it's also nice. Okay, our product. So our product is called Dion. It comes from humeur, which is a Dutch word for feeling or how you're. So what we do is to summarize is we measure stress in people with misunderstood behavior with variables and with interaction with clients. So we have in this case a smartphone. It can also be a notification system that the caregiver already uses. And we that's already told. So typically you can monitor it to any device on a smartphone or web application, or we can use an API to connect to existing notification systems, and it gives you a real-time insight into stress. And we have currently a couple of sensors, or wearables. So we have a custom developed. We developed our own food sensor. So it's like a wearable device that goes on. It sets integrated current electrodes to measure skin conductance mainly, and also heart rate. Now that's all trend. So if you measure when we have the wearables to measure the data, we also have to translate into stress-related information, and we find correlations into the signals and the stress outcome. I will come back to that. So what in the end we want to do is to create a better understanding in the client's emotions and behavior. We would like to reduce the amount of escalation. So when people if a client in a care house is agitated, he can eventually have a behavioral escalation where he can harm himself or others or the environment, and we'd like to prevent that as much as possible. So we send early warnings, which is like a real-time, caregiver, can you look at the client because he's building up tension or stress. That can also lead to self-management, so you can learn to understand the stress of yourself, but also of the client. So you can also, as a caregiver, if you're new in a group, it can be very difficult to understand the client. You can use the system to get more self-management in place. And of course, in the end, it also increase the trust relationship. So we really believe that this is not a tool that will replace care. It's just like a valuable tool to better understand and better build that relationship between client and caregiver. So we do that with a lot of partners. So we have around 25 care organizations on board, and the first one was Severinus. That's where we started, and we're currently scaling the product. So we are now also going from a quantified order, which is this product, to a quantified self-application, where, for example, also the Dutch police is interested. And we are currently approximately 200 devices live, and it's currently scaling inside care organizations as well. So was to get them all involved in a small pilot. It's also how we started and how we started development. So with small pilots, test the device, and get the care on board to help develop the device or the system. And right now it's going to scale also internationally. We're busy in Austria and also in Belgium and Germany to scale up the product there as well. Now then maybe a bit about our products. I've split into three topics. First of all, we have wearable development. So back in the day when we started the company, we started with off-the-shelf wearables like Batica E4 is a very known one. We started with the OpenBCI kit to measure brainwaves. We started with lots of different wearables or these signal sources, and we were looking for a golden set, as we call it. So how can we best measure stress, and also in real world environment. So if you, for example, have a client with an intellectual disability and use the OpenBCI kit to measure EEG, that works for 10 minutes and they take it off and they throw it away. So we need something widget, something that integrates, that is not, that the client preferably doesn't notice, it's very comfortable, and what preferably every client accepts in some way. So that's why we decided to measure heart rate and skin clocks on the foot, because the foot is like, it's quite far from the head and not that noticeable. If you have intellectual disability and you have a wristband, the two things can happen, or they like it and they don't show the real behavior anymore, at least for the first couple of hours or days, or they don't like it and they throw it away. You have cases where they throw it in the toilet and flushed it and then it's gone. So that's why we wanted something that integrates, and through literature and research and lots of testing, we found that the foot was the best place to measure our signal set. So we developed a custom wearable device. It's like a module now, but we want to make it smaller and integrate more. But now it's like a small module that measures, that's located on the ankle. I don't like to call it an ankle bracelet, but it's quite close to that actually. And secondly, we have a sock that measures skin conductance, so that goes over the foot. The electrodes are this is inside out, so the electrodes are inside of the sock, of course. And with the two pads on the bottom, we measure the skin conductance, and it's translated to the module above. With that, we get quite a decent signal of, at least this is really for IDA, to measure stress with.
May I ask you a question?
Yes, of course.
How do you measure the heart rate?
The heart rate is measured with a PPG sensor on the device itself. So it's
on the device itself?
Here in the back you can see a small PPG sensor. So and on the ankle is quite, it's actually quite...
you have good results there, because most of the time heart rate is not so accurate to measure in that part. But anyhow, it's...
But now we, with this setup we get like even sometimes a better signal than from the ECG wearable that we, not the medical one, but you like it to electrode ECG.
Yeah. And the reason why you don't want to call it an ankle bracelet is because the police is one of your partners.
Yeah, and they don't like to, so they actually use that officers, and if you say to an officer, hey, you want an ankle bracelet, they think you're criminal. So we try to, it's also called by customers, it's like the smart sock and the slim sock in Dutch. So that's typically how it's referred to. Then you get like a signal out of it, which is quite easy to use, but in the end we acquire quite easy signals. I see that the pizza's coming.
Maybe we should take a small break?
Yes, of course.
It's my
We are now all distracted, sorry.
How many slides do you still have?
Should we finish the talk first, or?
10 slides, I think.
10? Oh, okay. Can we finish it?
Yeah, we can finish it.
Alright.
So this is the data we get out of it. Now we have like currently quite an energy efficient device. We can measure for up to 2 days continuously, so 48 hours, one charge of battery. We now use it quite I think that's quite a nice operating system that makes it possible. That's what the part now. Then the part of data processing is also part of data science. So everything is built around the complex model of effect. So we want to we based everything on, you can measure arousal and valence, and in that circle you could plot any emotion. And currently focus mainly on arousal, which is the level of excitement. So how excited are you from a certain thing you experience in real life. And valence is more the positive or negative feeling behind an emotion. For example, if you're happy, it's more positive. If you're sad, it's more negative. And that's quite difficult to measure, so we're still working on that. But in the end, you would like to at least be able to say which one of the 4 quadrants is a person currently located, based on only wearable data. So to train the models, a bit of AI, we developed a reference database. So we have a lab at our office where we invite test participants to take part in a small test. So one test takes approximately 2 hours. We do different things in that. So it's like a bit of VR. We have to walk over a plank. And if you're afraid of heights, it's quite interesting to see your stress response. We do mathematics tests to get you like in some kind of state where you have to perform, and that creates arousal, and with that we train the models. And afterwards, because that's the main problem with the data we gather from care houses, that we don't have any labels, so we don't know how the participant or how the client is actually feeling. And if you want to train a model, you need some kind of reference. And to get a good reference, we relied on self-annotation of the participants in our lab, and that's how we trained at least the base of our models. So the models are working in this way it's quite simple, but actually it's quite complex. So we use neural networks. So we use an input, which is skinglux heart rate or acceleration in our case. Then we have a shared layer, which is like the layer we developed with the data from the lab. So we have one general outcome, which is the balanced accuracy, I think, is between 60 and 70% already, but we would like it to be a bit better. So then we use personalized layers where we fine-tune the parameters of the model to a setting where it becomes to 80 or 90% in between that number accurate to detect stress, like high levels of stress in your situation. And then we come with a prediction, and we translate it to very simple traffic light. Red is stress, green is no stress, and orange is there's build-up of stress.
How do we do the prediction? Is it based on scientific information from all your partners?
Yes, I come back to that. So
okay.
maybe first, so the first thing is you need clean signals. So if you have the sock and you walk, you get like noise in your signal. That's one of the disadvantages of using a sock. But with adaptivity noise, you can, for example, get quite a clear signal. In most cases, not everything. Also depends on how the sock is worn. But it gives you more control over the signal, and you can use it as an input. And then we extract features. So the model uses 2 types of features. So the first features are extracted based on scientific proven methods. So we did a lot of research into existing papers, what features from heart rate or skinglux they used to come with a stress indication, and we used those in our models. So we used scientific literature to find the best features. And then we also trained a convolutional neural network to find new features in that information. We use a combination of both to come with the best features for our situation, and that's combined in one model. Now then we applied it in care houses. This is actually an early example of a graph that we exported. So back then we used this to also come back to caregivers and show what we got. So what you can see is blue is detection and red is observer. So the observer gives in labels. So we used in an early situation a pilot study where we did very small pilots within care organizations. We asked caregivers or parents to observe and indicate what they were seeing with the client, and based on that we could build a model and come with roughly the same outcome that showed us that with a personalized model you could quite accurately predict or measure stress. So yeah, that's what we currently do. So now we have a stable model which is based on a convolutional neural network with with fixed features that we personalize by some analyzing. And afterwards, we would like to go to supervised learning, where we train a model based on labels we get in real time, and where we can iteratively get the model to a certain level where we find it suitable, and we can then maybe stop the supervised learning or continue it, but then we don't ask actively for labels anymore. So that's currently what we are working on this year. We want to have supervised learning as a new feature of our product, so we can better measure, or can get even better predictions with less interaction of the caregiver or the team at Mentec. And then we have, of course, the software itself. So we try to translate everything like we did with the wearable to a level where the caregiver can interact with it. So it should be simple, easy to use. And that, I think, is the main challenge of Mentec. So we built a platform that can stream the data in real time through the internet, where we run the models in the cloud, which outputs a stress level. That's then fed back to a dashboard where you can analyze the data in time. And an app. Well, the app is mainly based is actually acting in two ways. So the first way the app works is that we use it to connect to Bluetooth. So we actually collect the data via this app, and for example connect the sock, and then you can start measuring. It should be close to the client, which is actually quite linked to the system currently. So we're also working on an LTE version, which can transmit the data directly to the internet if necessary, or even locally. Now you have two ways we interact with caregivers. We have a diagnostic system where we use like time-based data on stress, and also the raw physiology to give like a time-based outcome or graph, and a behavioral scientist can use it, for example, on this interventions. So if you, for example, have a label, let's say okay, he was eating, and during the eating the stress was very high, then you can search where that problem comes from. So one case, for example, we had a client that was in the morning he was always escalating his behavior when he was at the kitchen table, and they didn't really know why, so he always got angry, and he was like unhandleable for the caregivers, and nobody knew what was happening and why he was getting angry. And at one point they were using the system, and they noticed that when they put like the caregiver came in the kitchen, and they put the plate on the table, the sandwiches on it, and they had like the peanut butter, like making a sandwich, and when they were she made the first sandwich, and she took the second one, and with the second sandwich, so they put a one on the side, second one there, and the client was looking at the sandwich, and he couldn't eat it, and that was causing a lot of discomfort, and it was like a short in his brain, like I want to eat, I want to have that sandwich. So what they now do is they make the sandwich in the kitchen, very simple, and they present it to him, and he can eat immediately, and the behavior is gone. So that's quite cool. That's typically the small things how we can add quality of life to these kind of people. And then we have the early warning. So this one is more for psychologists and behavioral scientists. This one's more for the caregiver themselves. So here we have this very simple app in which they can add all the clients that using the U, and they can have an indication on their stress level in real time. So it's green, orange, or red. And if it's red, you get a notification that the phone starts vibrating, even ringing, and they can go out to the client and calm him down. So that's also used in some situations. We had one, also to give an example, we had one situation where we have a client that could escalate any moment in time, so they were checking on his room every 10 minutes, like opening the door, hey, how's it going, and close the door. That every 10 minutes. You can imagine how intrusive it is in your own life. So they didn't want to do it anymore. And they're now using the system to if it starts getting orange or red, they go in the room and they calm him down, but they're not checking on him every couple of minutes anymore. And then the impact stories. So I think we are now managing to do early warnings based on stress predicted by human in a number of cases. We give insight into stress over time, and that results in more quality of life and better understanding for the client. And in numerous cases we changed the day schedule, and that created a better fit for the client caregivers. That solved a lot of behavioral problems. Yeah, maybe I already tipped it a bit with the quantified self and the police, but maybe as a close-off question, what kind of other use case do you foresee for the human? What can you imagine? That's it.
Thank you.
I could think of a few use cases.
Uh-huh.
Students have a lot of stress.
Yeah.
It would be really cool to see if all, for example, if all the students get the same stress level at a certain teacher or at a certain moment during a presentation. This could be interesting.
Seems like exam stress.
When the finals are coming.
Yes.
But what would you like to do as a caregiver? Because in this case, somebody sees the early warning signal of a student. What are you going to do? You give him a pot of beer or?
This would probably help the student, but not in the long run. But I would see it more as a tool for yourself than as a like the.
And neuro adaptivity and brain hacking. I'm looking forward to it.
All right. So
Go ahead,
this is not a very polished talk like yours. So it's kind of like a hack together presentation. So let's see. Let's keep it informal. If you have questions, just ask. It's kind of meant as an academic kind of talk. I do run a startup, and I'll briefly mention what we're doing at the end. But mostly, it'll be kind of like academic sort of technical topics. Hopefully, it'll be kind of interesting. So just briefly, my background, started coding when I was young, 8 years old or so, got into like neural nets, brains and whatnot. Did a PhD in that at some point a few years ago. And now, we're building a startup, which I'll mention a few things about later. But anyway, 3-part talk, neurotech versus neuroadaptivity, how to understand brains, and then how to hack brains, which is really brain hack. Excellent. That's the meetup, right? So, okay, so neurotechnology, right? So what is neurotechnology? It's obviously you can do like brain imaging, you can do brain stimulation, that kind of thing. And it's kind of obviously neurotechnology because it's neural signals and whatnot. And then you have obviously the intracranial stuff, that's clearly neurotechnology, right? And then you have this non-invasive stuff, the EEG, ears, and so on. But then heart rate variability from a wearable, is that neurotechnology? What do you guys think?
Yes.
I think it is, right? Because it's kind of a proxy signal from the brain, right?
Your brain and your heart are a little bit connected, eh? So it is.
They're a little bit connected, yeah. Exactly.
And every bio signal is neurotechnology.
Yeah, more or less, yeah. I think so. So then if you do like, so we're doing speech and motion recognition of mind, as also heart rate variability. And that's kind of a neural signal. It's pretty close in some ways. And like, why is that important? Why am I telling you that? Basically, because they're much easier to track. A lot of these signals, they're much easier to track than EEG, ears, fMRI, all this direct brain signals, right? In the real world. So are you guys all technical? Like, just kind of gauge the level and what's the background of your technical?
I'm a physics PhD.
Physics PhD. Can you guys shout like technical, non-technical? Who knows what? I don't know. Who knows what FFT is?
Fourier transform. Fast Fourier transform.
Frequency stuff, yeah. Okay, so anyway, the idea is right that a lot of signals are easier to. Actually, where I can point this. There we go. So the idea is this stuff is easier to measure, right? Than neural signals, and it's a transduced version of the neural signals. So why not just measure this stuff? And that's various signals are more or less close to the brain signal. That's kind of the idea there. And so that brings me to neuroadaptive systems. A neuroadaptive system is one that adapts to a person's neural state in real time. So for a system to adapt your neural state in real time, it has to measure it. You have to do the real-time measurement, right? So I have this sort of taxonomy of the field. and I think it's not entirely correct, but it's more or less right. So you have biofeedback, which is it's not all entirely neuro related necessarily. Some things are sort of outside of not that close to neural signals. And you have neurofeedback, and then you have neurotechnology, which is not used in a feedback sense, right?
Neurofeedback is when you try to change the brain.
Yeah, exactly, in some way. So for example, you show someone's alpha signal or alpha power or something, and you can learn to control that, right? You can learn to
And neuroadaptivity, so what is that?
Yeah. So neuroadaptivity is like I said, when you have a closed loop system, right? So you're doing measurement. I think I have a picture of that, maybe. Nope, I don't have a picture of that. Not on this one. You're doing real-time measurement. It's a closed loop system. Then you do some kind of intervention. You then measure the effect that had, and then you tweak the intervention, right? Okay, in real time.
Okay.
Yeah.
It's a control system. Oh,
Yes.
neurofeedback is.
Yeah, exactly. Right. So, I mean, usually if you're doing this stuff, multimodal tends to be better, right? Multimodal is almost always more accurate. So if you, for example, look at EEG studies for emotion recognition, you typically have like computer vision. You have computer vision approaches. You have EEG approaches. And then if you combine them together multimodally, it's almost always better, right? So that's not surprising. But it turns out that they pick up slightly different signals, right? So they all have issues with them. So EEG, for example, there's a lot of different kinds of noise, and it's hard to work with in the real world, which is another reason. Yeah.
Is phase an EEG with visual recognition like
So EEG?
or EMG is a
Oh, EMG, yeah. So it's muscle.
Phase muscle
Yeah.
Face. He's asking about the face.
Oh, the face. No, that's computer vision.
Oh.
In this case, it's computer vision.
Is there correlation between the two? So if you have alpha and beta, etc.
There's
waves.
correlation between the two, yeah. But there's also some independent signals here. So I think that's kind of this one's kind of interesting. On an individual level, actually, valence arousal are quite correlated. You probably know that, right? But on a statistical level, on a population level, they're not. You get basically they're fairly independent when you have enough people. That's kind of interesting. Let's skip over that slide. So, sorry, I will quickly put these slides together. There was supposed to be some other slides after this. They're not there. So the whole thing about neuroadaptivity, which is really great, is that you can have much more effective interventions, basically, right? Because they're close to why? Because they're tailored to your actual state, right? In the moment, because you're measuring and then you have the intervention and it's.
But you need.
I used to have a nice diagram, but it got chopped.
But you need the neurotech for doing neuroadaptivity. I mean.
Yeah,
because that's
you
basis.
do.
That's
If you
basis.
consider this neurotech, then yes, I mean you need something, right? You need something to
Yeah.
measure in real time. You can do it hard, yeah, you can sense it.
But when you say about the adaptivity itself, does it mean that practically you're introducing change in the behavior of the human? Or you just
Typically, you don't have to.
Looking from the other perspective, you don't have to do the change in the human, just do different parameters. More adjusting the threshold to yourself based on the person itself. So you do like the base measurement, because if you are auditing somebody, then it's different reaction to different people. And if you are just observing natural behavior, then just parameters are different. But still, there's no influence on the person who you are actually observing.
So the point is, do you have to tweak an intervention towards a person, or can you tweak something else?
Parameters, yes. For
It doesn't have to be something that affects you, of course. Yeah. So like we're doing stuff with the startup with mine. We're doing stuff in cars that does affect the person. Like you can do. Yeah. I'm not sure what a use case would be where you're not affecting a human being, right?
Yeah, if you're really like a person in the loop inside of your system, it's better to just change the parameters around based on the reaction of the person to the situation.
No, that's exactly the point. Yeah, exactly. You measure that reaction to the person, right?
Yes. So that just is baseline for him, just to show some images and see how it reacts. It's just getting the baseline.
Yes, doing that in real time.
Yeah.
Yeah, exactly. That's the point. The real timeness is kind of the point. Yeah. Okay, so moving on, bunch of slides, how to understand brains. Do you, any neuroscientists or like biologists, or maybe you learn something here. So, right, so there's different ways to measure brain signals. You have like cellular stuff. This is quite interesting. You have calcium imaging, 2-photon microscopy. This is interesting if you're trying to understand sort of circuits that are, microcircuits, right? This is a hippocampus, I think, from a primate of some kind. Might be a mouse. Then you have, that's everyone's favorite molecule. If you're a techie, you're probably drinking caffeine all the time, right? So that's your favorite drug right there. And then you have fMRIs. You go into a big machine. You probably most of you probably know it has really good spatial resolution, but not great temporal resolution. EEG, MEG, great temporal resolution, shitty spatial resolution. ECOG is great temporal. It's basically, ECOG is like EEG inside the skull. So you open the skull and then you put some electrodes in the surface of the skull, which is great for, again, for a lot of purposes.
For deaf people.
Data quality is very good.
It's great tech, man. You want this. You want this in your brain. So, but brain signals are quite complex, right? So this is a 32-channel EEG, and this is like a typical EEG analysis software, which is EEG Lab. So how do you understand brain signals, or really any other kind of signals? Well, you have heart rate signals, and you have some kind of rhythmicity, right? And then you have other kinds of signals, the kinds that you guys are using. So like you have EDA and so on. And the reason I mention FFT is because if you know FFT, you're like, you can work with almost any kind of technical system, right? That has periodicity, and it's. So who doesn't know what FFT is? Okay. Anyone else? Okay, so if you have a sine wave, I think this is kind of useful to know, maybe interesting as well, but if you have a sine wave, you have a certain frequency, obviously, that it's repeating at, and then here you have another sine wave that's much faster. If you combine them, you see a slightly more complex wave. That's basically just, you add up, every one point, you just add it up with this one, and then you get this one, and then you add up all the points, and you get this wave. So then if you do an FFT, you get these two peaks here, which tell you what frequency sine wave basically what frequency of signals you had over here. That's kind of interesting because it applies to the brain. So that's a typical EEG spectrum, which shows you like the different bands. So you might have heard, if you're ever working with neural data, that you have the delta, theta, alpha, beta, gamma. These are like different ways of subdividing the frequency of brain activity. And they all kind of correspond roughly to different types of functions in the brain, sort of. It's a little bit more complicated than that, but sort of. And then you can look at that from different parts, from different electrodes, right? So if you have an EEG hat, maybe I'll show it. So you have different areas, right, where you can record from different electrodes, and then you can do this FFT, where you basically decompose a signal like. Yeah. Exactly. So you can measure signals from each of these locations. And then you do an FFT and you can see the relative activity at that location. And typically, for example, if you close your eyes, alpha activity goes up. And that's, in a healthy person, you can pick up stuff like that with FFT. Does that make sense?
Yeah, it's really more that if you look at the time domain itself,
Yeah.
if you're using the samples, just those samples itself actually goes to FFT.
That's right, yeah.
So it's just simpler to understand your data is being as acquired, so the amount of data being processed is actually less without losing much in the point itself. So it becomes kind of cheaper for your process, it becomes simpler to understand what you're actually doing. So they are kind of
Sometimes it's simpler, sometimes it's not, yeah.
Yeah, it
Depends what you're doing.
If you compare to the time domain, it's always simpler. Even at the selector. I didn't see any situation where it will be
Yeah, I mean, sometimes you want to work in a time domain, but sure, yeah. Depends what you're doing. Okay, so that's, anyway, some math, skip over it. If you know what it is, you know what it is. But the point is, it's very, you can do this very efficiently. And like he said, it's some things are much easier to do in the frequency domain. And it turns out, usually if you're analyzing brain signals, you look at the frequency domain response. So another reason FFT is kind of interesting and important also for non-brain signals is if you're designing filters. This is like, you might want to, for example, say, I don't want signals over here, I don't want signals over here, I want to keep the signals in a certain range. And then you have a filter, and then you have different filter responses basically. And the point here is that the way that FFT works is that you can never have a perfect filter. You get this thing called ringing. Yeah. Does that make sense? Any questions or? No. No. Okay. One other interesting thing is that if you look at the brain signals, if you look at kind of the spectrum, it shows what's called a 1/f kind of characteristic. So if you plot in a log-log plot, you get a straight line, and that's characteristic often of like critical systems that are close to criticality, which is kind of interesting. Well, moving on, too much details there. One other thing here that I think is worth kind of mentioning is. Well, it's kind of interesting as well, maybe if you're interested in math, is if you do a Fourier transform of a Gaussian, you get a Gaussian. So if you have a signal that's narrowly located in time, for example, then you need a lot of frequencies to represent it in the frequency space. So you get this kind of like spread out Gaussian. And then conversely, if you have like a widespread Gaussian, you get more. Is that right? More or less. Anyway, the reason that's important is that basically you have a limit on the precision with which you can know your signal in time or in frequency. So there's a bunch of different ways to deal with this. There's like wavelet transform and different techniques that you can use. So in terms of hacking brains, you can there's transcranial magnetic stimulation, which where you basically you have this quickly changing. You basically run a strong electrical current through a wire loop, which generates a quickly changing magnetic field, which then generates current in the brain. And so you can target quite specific brain areas for that. And that lets you stimulate or inhibit parts of the brain. And then you can make people move their arm. You can treat depression. It's actually used for quite a few things as well. Another technique is transcranial current stimulation, where you basically run a current through someone's scalp. It's fairly safe, you know, and quite simple. There's one approach is where you just run direct current, which kind of looks like that. You ramp it up, you stay constant the current. Another approach is alternating current into the brain. This is more complicated, but it's more interesting because you can basically tweak specific brain circuits when you at specific frequencies.
What would you typically use this for?
It's being used, for example, in military training for accelerated learning. It is being used also in treating depression and just different kind of.
Yeah. Would it be possible for me to get a hold of this stuff easily?
Yes, I have a story on that. You can easily build it. I built a version at a hackathon. I built a version myself in 8 hours or so. So you can build it with like a Raspberry Pi and some stuff.
And I want to fry my brain.
If you don't want to fry your brain, you can buy a device. This is CE certified, clinically validated. It's a startup, but then you gotta pay for it.
Might be worth it.
There was a startup that had a patch you could just put on your head, turn it on, and it would help you concentrate.
So you're talking about this one?
Yeah.
You don't will not focus, or?
No, it was another one. It was just a patch. But maybe this one. No, go ahead. Maybe this one was well. Can we?
Well, this is a different one. This one is quite cheap, and it's also it's like $300.
Are there more fashionable alternatives?
This one?
But I don't let's go.
Alternative facts.
That's the thing with things on your head. They're generally not so fashionable.
Yeah, yeah.
They also had this thing, it was called the Happy Band, maybe some of you saw it. It was like a band you put on your neck, and then you had an app, and you could choose what kind of emotion you would like for the day. And that it would generate like some kind of field, and it was, well,
Oh, really?
it was sold many times, and I think they made a lot of money on it, but, well, if you see it,
Recently, or?
yeah, well, I think it was a few years ago, like this. Strange thing, yeah.
Yes.
Yeah,
Yeah, you can get in that area.
yeah.
Then there's nootropics, which is kind of also quite interesting. AKA smart drugs. There's some of the popular ones. This one is banned in Olympics. So like this stuff works. So much so that it's banned in Olympics. So, and then transcranial ultrasound is quite an interesting one, but you can't really do it yourself, and I wouldn't recommend it.
You blow up your
It's,
brain.
By the way,
it can be dangerous. Don't do it yourself. But it's interesting clinically and sort of in research settings.
getting back to
Yeah.
the thing that was banned in the Olympics.
Okay.
If
yeah,
I think
yeah,
of
Sorry.
if I think of the brain, I think of cognition.
Yeah.
The Olympics, you mostly, of course, you also require your brain to stimulate your muscles. But why
is it
so
banned?
effective? Yeah.
It improves reaction time and
Okay.
kind of that sort of thing.
Good for gamers.
Yeah.
But yeah, you can get these three. It depends on the country and the legalities, but you can get a lot of this stuff over the counter. Any questions on that part? Otherwise, a couple of quick slides on my startup and what we're doing. So what we're doing at mine is basically where we have a platform, software platform that it's neuroadaptive and helps to bring personalized well-being at scale. And we basically measure your psychological, physiological state through speech or wearable data. Then it goes to the cloud. We make predictions and recommendations that are continuously tweaked, and that's the diagram I was looking for earlier. And that's your closed loop. And it more or less works today. We're working with some we have a couple of use cases. We're working with a couple of high-profile clients, like Porsche, for example, in the in-car setting. Is there a car there? No, yeah, there's a car. Yeah, so that's what I'm spending my time on most of the time, trying to bring this to the real world, basically. So neuroadaptivity in sort of real-world settings. And yeah.
So what's the goal then, in the end?
What's the goal with this, or?
Yeah, can you give some examples, like in the car, what do you want to achieve with the user?
Relax them, make them feel happier, basically tweak their state to the state they want to be in, within the states that we
Or
can
to be
track.
more focused on the track?
We're not really working that direction, but that's obviously something you can do, right, for safe and
So
safe
there's-
systems, yeah.
What type of loop do you use for this, for instance, this car driver? What is the
Speech and heart rate variability.
yeah, but what is the loop back?
How do we affect the user?
Yeah, what is the neurofeedback? So what's the carrier to go back?
Sound, light, temperature, just different, whatever we can control in the car.
What is your ideal client for what you're developing at Mind? But am I pronouncing it correctly?
That's a difficult question. We're trying to figure that out right now.
Okay.
But probably well-being companies with apps of their own. Possibly hardware companies in the well-being space.
Well, first of all, I want to say that this was very interesting to me. And one of your last slides, not this one, no. Yes, this one. Yes, I thought it kind of also became an ethical question, wherein how much do you want to influence people's behavior? Of course, I get it in the car. If, for example, you get back from work, you're stressed, and well, your car helps you calm down. Yes, this is really nice, but what if people, I don't know, people they make something that influence you to be angry, or and there are many questions around this, I think.
There are many questions around it, yeah.
I have a question on his line. Where would you stop? Huh? Where would you stop?
Where would I stop?
Because
Question, that's also a
what
good
happens
question.
if a guy comes, I have this fabric.
Yeah.
I want these fucking workers to work whole day without stop.
So
Fuck their bodies.
No,
Fuck
I
their
agree.
bodies. We control their mind. Fuck their bodies.
I
They
haven't
won't
answered that.
eat. They won't work till they die. I don't care. Another will come.
it's a fair question. My answer to that is that if you're not tracking the user's state, then you don't know how technology is affecting the users right now. Right now, Facebook and social media, all this stuff is affecting you, but you don't know the exact effects it's having on you.